Hi and welcome to the 20th part of this C# for Beginners course. This tutorial will focus on C# interfaces. In this C# for Beginners course, we have covered the three main aspects of object-oriented programming, namely encapsulation, inheritance, and polymorphism. Links to the tutorials on these topics have been included below in the description. Another important aspect of object-oriented programming is abstraction. In C#, abstracting general rules and functionality before implementing functional code logic detail when constructing an application can be achieved through the use of abstract classes and interfaces. In this tutorial, we are going to focus on interfaces. In the context of object-oriented programming, abstraction essentially involves the separation of design implementation from concrete code logical implementation. So interfaces and abstract classes can be used in C# to implement the design of an application in code. The design on its own, however, is meaningless without the appropriate functional logical code implementation detail. Abstracting code so that types are loosely coupled can provide a flexible and extensible design for your applications. Right, let's explore C# interfaces through a code example. Let's first create a project using the console app.NET Core project template. I'm going to name this project Interfaces Tutorial. So the theme of this code example will relate to a construction company. Please remember to like, subscribe, share, comment to support the channel. It will be greatly appreciated. Let's start with a basic class named Employee. And let's add some read-write auto-implemented properties to the Employee class. Notice that these properties all have both get and set sections, which means the calling code can both read values from these properties as well as assign values to these properties. So as you can see, the getBasicInformation member is a method. The function of this method is to serialize certain property data and return this data to the calling code. So let's test the employee class by writing code in the main method to instantiate an object from the employee class and assign appropriate values to the properties contained within the employee class. Let's then write code to call the getBasicInformation method and write the returned string value to the console screen. Let's run the code. And you can see the property values are written to the screen in the format that was coded in the getBasicInformation method. Okay, so in this application, we want to include many types of employees that you may find in a construction company. We can encapsulate the employee types within appropriate classes based on the employee's respective roles. For example, we could have a class named Crane Operator and a class named Electrician to encapsulate data and behavior for each of these types of employees. But there's certain common data and behaviors that can be applied to all employees regardless of the employee's respective roles. So how can we ensure that our application reuses functionality across multiple employee types? Well, we can start by abstracting a common interface for all employees within the construction company. In code, this can be achieved by creating an interface. So creating an interface in code is very similar to creating a class, but instead of the class keyword, we use the interface keyword. And notice that no code implementation is included for any of the interface members. The interface only provides the property definitions and method signatures. And also notice that no access modifiers are applied to the property and method definitions. This is because by default, interface members are all public. So the naming convention for an interface is that a capital I should be included at the beginning of the interface name. In this example, our interface name is IEmployee. The I prefix is capitalized, signifying that the C# type is an interface, and the subsequent part of the name contains more descriptive text about the nature of the interface, which also begins with a capital letter. In this case, capital E for employee. When an interface is implemented by a class or struct, the class or struct is obligated to implement code logic for each of the members included in the interface. So you can think of an interface as a contract that must be fulfilled by any class or struct that implements it. A developer can include the following member types in an interface: methods, properties, indexes, and events. In this course, we have covered methods, properties, and indexes. Events will be discussed in an upcoming tutorial. In this tutorial, we'll focus on two of these member types, namely properties and methods. In the tutorial on C# inheritance, we discussed that in C# and .NET, only single inheritance is permitted, i.e. a class cannot directly inherit from more than one class at a time. This rule does not apply for a class or struct implementing interfaces. A class or struct can implement code for multiple interfaces. Note that an interface is able to inherit from another interface. If, for example, class A implements code for interface IA, and interface IA inherits from interface IB, class A must implement code for all the members of both interface IA and interface IB. So as stated in the beginning of this tutorial, an interface contains the design structure for those classes or structs that implement code for the interface. An interface on its own is meaningless. Let's prove this. Let's try to instantiate an object from the IEmployee interface. The C# compiler immediately flags an error stating, cannot create an instance of the abstract class or interface IEmployee. An interface only becomes meaningful when a class or struct implements code for each of the interface members. The interface provides a design abstraction that can be applied to multiple classes or structs. The interface enforces a rule that all classes or structs that implement an interface must implement code logic for all of the members contained within the relevant interface. So in order to make our IEmployee interface meaningful, let's implement code for its members in the employee class. So let's comment out the current members of the employee class. Let's then write the code whereby the employee class implements the IEmployee interface. And you can see that the code is similar to when a class inherits from another class. A colon follows the class's name, and this is followed by the name of the interface. And now red squiggly lines appear under the IEmployee interface name in the class definition for the employee class. And if we hover our mouse pointers over the red squiggly line, the C# compiler presents us with a message that lists all the members of the IEmployee interface that we must implement code for in the employee class. So let's click Show Potential Fixes, then Implement Interface. As you can see, Visual Studio has provided default implementations in the employee class for each of the members of the IEmployee interface. Each of the current implementations provided by Visual Studio force a not implemented runtime exception to be thrown. So let's create auto-implemented properties for each of the property definitions contained in the IEmployee class. We could implement code for each of the get or set methods of any of these properties. For example, if we wanted to ensure that a string value assigned to the job title property is valid, where it cannot exceed a maximum length of 50 characters and must not be less than 2 characters in length, this can be implemented in the set method. This tutorial is focused on interfaces, so I'm going to leave these properties as auto-implemented properties. Let's move on to the getBasicInformation method. Let's implement code so that the getBasicInformation method returns a string in a custom format. This string contains values for the ID, job title, first name, and last name properties serialized, whereby each property is represented on its own line with an appropriate property label followed by a colon preceding the value currently assigned to the relevant property. So we've implemented custom code for the getBasicInformation method. Another class implementing the IEmployee interface could implement this method differently, and this will be demonstrated a bit later in this tutorial. But each class that implements code for this method is constrained by the interface definition for this method, where the implementing method must be named getBasicInformation. The method must not accept any parameters and must return a string value. So let's go to the main method and use the IEmployee type to define a variable named emp, and then instantiate an object from the employee class using the new keyword. Note that you can say the employee class is of type IEmployee. Let's run the code. And that is an expected result. The employee class is of type IEmployee because it implements the members of the IEmployee interface. As demonstrated earlier, you cannot instantiate an object directly from an interface, but you can instantiate an object from a class that implements the relevant interface. So let's go more into the significance of abstracting functionality that can be applied to multiple types. Let's create another class and call this class Crane Operator. This class represents an employee whose role in the construction company is that of a crane operator. Let's go to our main method and test the crane operator class. And we can literally just replace the code new employee with new crane operator, because the crane operator class also implements the IEmployee interface, which means they have exactly the same type definition. The crane operator class and the employee class are of type IEmployee. So let's run the code. And this is an expected result. So let's say we want to extend the crane operator class by adding a new method. This public method returns an integer and accepts no parameters. The method's function is to return the number of full years that the employee has worked at the construction company. We can calculate the full years worked by an employee by simply finding the difference in years between the current date and the value assigned to the join date property, which, as the name implies, refers to the date when the employee joined the construction company. I'm not going to go into the detail of how this code in the getFullYearsWorked method works, as I want to maintain the focus on C# interfaces. So let's test this functionality in our main method. And the difference in the number of years between the time when this video was recorded and the employee's join date, which is the 12th of April 2011, is 8 years. Great. So let's create a class to represent another type of employee that works for the construction company, namely an electrician. Let's implement code for each of the members of the IEmployee interface for the electrician class. Let's go to the main method and test the code. And notice how when we define the emp variable, that we need to define it as the electrician class and not the IEmployee interface. This is because we want to call the getFullYearsWorked method on the emp object, and the IEmployee type does not contain a definition for the getFullYearsWorked method. So we need to define the variable with the electrician type in order to see the getFullYearsWorked method in our code editor. Right, let's run the code. And this works fine, but our code implementation is not ideal. We are repeating the same implementation for the getFullYearsWorked method in both the crane operator class and the electrician class. How can we ensure that this repeated code is only written once, which is a key objective in object-oriented programming? So to achieve this, we can make the employee class that we created earlier into an abstract class. We can implement the code for the getFullYearsWorked method in the employee abstract class, which will mean this code can be accessed from any class that inherits from the employee class. So we can now change the crane operator class and the electrician class to inherit from the employee abstract class. Now that the crane operator class and the electrician class both inherit from the employee abstract class, we can get rid of the code implementations that these classes are implementing for the IEmployee interface. This is because code implementations for members of the IEmployee interface are now consolidated in the employee abstract class. And let's ensure that the getYearsWorked method definition is added to the IEmployee interface. And we are now able to change the declaration code and instantiation code to IEmployee amp equals to new crane operator. The getFullYearsWorked method is in one place and is available to any class that implements the IEmployee interface. We have made the employee class an abstract class that implements the IEmployee interface. This means that future classes representing employee types added to this application can simply inherit from the employee abstract class to ensure a consistent design across all employee types. Functionality common to all employees can be consolidated in one place, i.e. the employee abstract class. If code is modified in the employee abstract class, this modification will automatically affect all the other classes that inherit from the employee abstract class. So let's create another class representing another employee at the construction company, the drywall installer. As you can see, the code is clean and easy to implement because we have abstracted common functionality for an employee through the use of an interface and an abstract class. So let's test our new drywall installer class. And the result is as expected. We are now able to create employee classes by implementing a small amount of code, and they will automatically inherit the common functionality implemented in the employee abstract class and the structure established in the IEmployee interface. Let's create two employee classes representative of employees that are at the managerial level in the construction company. So let's first create a class representing an employee whose role is that of a project manager. Let's say that all managers in the construction company have their own offices and each manager has a secretary. So a manager is also an employee but requires additional data. The project manager is a manager but is also an employee, so the project manager must inherit from the employee abstract class. And then we can extend the project manager class by adding the additional properties that are unique to employees who are also managers. So let's reflect this by adding two properties to the project manager class. Let's add the office ID property, which represents an office location. This property is of the string data type. Let's add the secretary ID property. This property contains the ID of an employee, so this property will be of the integer data type. Let's add a class representing another manager. This class represents the position of safety manager. Let's name this class Safety Manager. A safety manager is of course an employee, so it must inherit from the employee abstract class. Let's add the two additional manager-related properties, namely the office ID property and the secretary ID property. And it is clear we are repeating these two properties for employee classes who are also managers. So we can abstract these two properties by creating an interface. So let's create an interface named IManager. As discussed in previous tutorials, in C# it is not possible for a class or struct to inherit from multiple classes at one time. But in C#, a class is able to inherit from one class, but in addition to this, is able to implement as many interfaces as is deemed necessary. So our Safety Manager and Project Manager classes are able to inherit from the Employee Abstract class as well as implement the IManager interface. So we want to include two new properties, Office ID and Secretary ID, in the information outputted to the console screen as part of the serialized string returned in the getBasicInformation method that has been implemented in the Employee Abstract class. Because the getBasicInformation method is a virtual method, we can override this method. We can use the base keyword to call the getBasicInformation method in the Employee base class, and we can then concatenate the values of the Office ID and Secretary ID properties to the string returned by the getBasicInformation method in the Employee base class. The code in the overridden version of the getBasicInformation method will return standard employee property values as well as standard managerial related properties to calling code. So we don't want to repeat this code implemented for the overridden getBasicInformation method for all managerial related classes. So we can facilitate the reuse of this functionality by abstracting common manager-related functionality into an abstract class. Let's call this new class Manager. So the Manager class will be an abstract class that inherits from the Employee class as well as implements the IManager interface. And we must implement all members of the IManager interface because, as discussed, when you implement an interface on a class, you are imposing a rule on the relevant class that all members of the relevant interface must be appropriately implemented. And now any manager-related class that is added to this application in the future can inherit from the Manager abstract class, which encapsulates the common functionality required for manager-related classes. Okay, so let's write code in our main method to test the Manager class. Let's run the code. And you can see that both functionality in the Employee class that implements the IEmployee interface and functionality in the Manager class that implements the IManager interface is utilized by the calling code on the Project Manager object in our main method. And for good measure, let's also test the Safety Manager class. Great. So let's go up a level in the management hierarchy and create a class named Chief Executive Officer. So although the Chief Executive Officer is at the top of the employee hierarchy, the Chief Executive Officer is also both a manager and an employee. Unlike a manager and an employee, let's say the Chief Executive Officer has a personal assistant, and we want to extend the Chief Executive Officer class by adding a property that will store the ID of the Chief Executive Officer's personal assistant. So we could have the Chief Executive Officer implement the IEmployee and IManager interfaces, and then extend the functionality for the Chief Executive Officer class by adding a property that stores an ID reference for the Chief Executive Officer's personal assistant. But we have already encapsulated functionality for managers and employees in the Manager abstract class. So in order for the Chief Executive Officer class to inherit functionality for a manager and an employee, we only need to write code for the Chief Executive Officer to inherit from the Manager abstract class. We can then extend the functionality of the Chief Executive Officer class by adding the Personal Assistant ID property. Let's create an interface representing functionality unique to a Chief Executive Officer. So let's create an interface named iChief Executive Officer and add the Personal Assistant property definition to the iChief Executive Officer interface. Let's then write code so that the Chief Executive Officer class implements the iChief Executive Officer interface. And then, of course, let's fulfill the contract whereby we must implement the members of the iChief Executive Officer interface. In this case, there is only one property member to implement. We can then override the getBasicInformation method and concatenate the value stored in the Personal Assistant property to the string value returned from the Manager abstract class's implementation of the getBasicInformation method. Let's write code in the main method to test the Chief Executive Officer class. And this demonstrates that the functionality in the Chief Executive Officer, Manager, and Employee classes is working as expected. And you can see how we've been able to reuse common functionality across multiple types. This highlights the advantage of appropriately abstracting common functionality. The code is clean, easy to maintain and reuse. So now that we have a basic structure created for our application through the utilization of classes, abstract classes, and interfaces, let's create a more substantial code example to test this code infrastructure. So firstly, let's create a method in our program class that will be called in the main method and will create an in-memory store of employees. So let's name this method seedData. It does not return a value, so we use the void keyword to signify this. The seedData method must be static so that it can be called directly from the static main method. The seedData method contains one parameter named employees. This parameter is a strongly typed generic list. This is made clear in the parameters type definition, where the list type definition code for the employees parameter includes the IEmployee type within greater than and less than symbols. We are about to demonstrate how using the IEmployee interface to strongly type the employees list enables the loose coupling of the list with all of our employee types. It is better to use abstractions for type definitions. If, for example, the employees list was strongly typed as the Chief Executive Officer type, we would only be able to store objects derived from the Chief Executive Officer class in the employees list. This would in effect tightly couple the employees list with the Chief Executive Officer class. By using the IEmployee abstraction to strongly type the employees list, we have created flexibility in our design and room for extensibility. We have loosely coupled the employees list with our employee objects. So let's create an object derived from the Chief Executive Officer class. Let's assign appropriate values to the object's properties and then add the object to the employees generic list. Let's create an object derived from the Project Manager class. Let's assign appropriate properties to the Project Manager object and then add this object to the employees generic list. Let's create an object derived from the Safety Manager class and repeat the process. So let's create an object derived from the Crane Operator class. And let's say there's a requirement to extend the functionality of the Crane Operator class. So the requirement is that for certain jobs that a crane operator is assigned, a certain percentage is added to the crane operator's salary. Let's say that the justification for this increase in salary is that many of the crane operator's tasks are more dangerous than the tasks assigned to employees that occupy other positions. So let's extend the crane operator class by adding a method named getDangerPayIncrease. And to keep things simple, this method will return a decimal value representing a 4% increase. So now let's make the annual salary property in the employees abstract class a virtual property. And then let's override the annual salary property in the crane operator class so that we can add the danger pay increase amount to the crane operator's salary. So we have just demonstrated here that when an interface member is implemented within a class, that the implemented member can be written to include the virtual keyword, meaning that derived classes can override the relevant member. And let's include the annual salary property value as part of the string value returned by the getBasicInformation method. Note that this modification of the getBasicInformation method's returned string will propagate to any derived class that inherits from the employee abstract class. So now the annual salary property will be included as part of an employee's basic information for all employees in this application. We have modified the code in one place, and this modification will affect multiple implementations across many classes. This highlights the benefit of abstracting common functionality and facilitating code reuse. Okay, so let's assign appropriate values for the properties of our crane operator object to our seedData method. Let's then create two more objects, both of the electrician type, and add these objects to the employees generic list. Note how C# allows us to create a multitude of object types, and because all of these types implement the IEmployee interface, we are able to store these objects in a list that is strongly typed as the IEmployee type. So we are able to do this because these objects are derived from classes that implement the IEmployee interface. And this enables employee objects of types that may have evolved quite differently, for example, an object of type crane operator and an object of type chief executive officer, to be added to the strongly typed employees generic list. Just to emphasize that this is possible because the chief executive officer class and the crane operator class both implement the IEmployee interface. These classes are both of the IEmployee type. So let's create another method in the program class that basically implements code to call the getBasicInformation method on any object derived from a class that implements the IEmployee interface and writes the employee's basic information to the console screen. This method is named WriteEmployeeInformation to screen, does not return a value, and accepts one argument of type IEmployee. So this method is able, for example, to accept objects of type crane operator, objects of type safety manager, and objects of type chief executive officer. Basically any object that implements the IEmployee interface. We have loosely coupled this method from our employee objects by defining the employee parameter as the IEmployee type. We have achieved this loose coupling effect using an abstraction to define the employee parameter. Here we can see an example of an interface being applied to facilitate code reuse. And let's write a method that outputs a header to the screen. Let's call this method from our WriteEmployeeInformation to screen method. Let's then create another method in the program class that facilitates a basic navigation mechanism so that the user can navigate through the employees list using the right and left arrow keys. So let's call the code from the main method. Just a reminder that all code created in this tutorial can be downloaded from GitHub. Please see a link to the appropriate repository below in the description. Right, let's run the code. Let's navigate through the employee information using the left and right arrow keys. And notice that the additional danger pay has been added to the crane operator's salary. The annual salary for the crane operator was assigned a value of 50,000. The overridden annual salary property in the crane operator class adds an additional 4% to the value initially assigned to this annual salary property for the crane operator. So the annual salary displayed to the screen for the crane operator is 52,000, which is the correct amount. Great. So just to summarize what we have discussed and demonstrated in the first part of this tutorial on C# interfaces. We discussed that an interface contains definitions for a group of related functionalities that a class or a struct can implement. We discussed that by using interfaces you can, for example, include behavior from multiple sources in a class. Interfaces should not contain code implementations. However, note that in the next part of this tutorial, we'll discuss that from C# version 8 and onwards, default code can now be implemented for interface members. This default implementation functionality was introduced in C# version 8 so that newly added interface members do not break existing client code. Interfaces can represent to calling client code what the classes and structs that implement their members are able to do. More than one interface at a time can be implemented by a class or struct. This is unlike inheritance for classes, where only single inheritance is allowed. An interface is like a contract. It is an agreement that when a class or struct implements an interface, all members of the interface must be implemented in the relevant class or struct. An interface can inherit from other interfaces. If, for example, a class implements an interface that inherits from other interfaces, that class must implement code for all members, i.e. for the interface included in the class's definition and the interfaces from which the interface included in the class's definition inherits. The C# member types that can be included in interfaces are methods, properties, indexes, and events. In part 2 of this tutorial, we'll discuss the new functionality added in C# version 8, where default implementations can now be included in interfaces. So in this tutorial, we looked at implicitly implemented interfaces. In the next part of this tutorial, we'll discuss explicitly implemented interfaces. We'll continue with the example demonstrated in this tutorial and demonstrate how to implement interface members explicitly. Please like, subscribe, share, and comment to support the channel. It will be greatly appreciated. And please ring the bell so that you can be notified of future content, which will be coming soon. As always, all code in this tutorial can be downloaded from GitHub. A link to the relevant repository has been included below in the description. Thank you and take care.